Of course, down is on. Okay, welcome everyone. Last class I kind of didn't intend to have a class, but enough people showed up that I presented one of the topics anyway. And then I thought I would just do the same thing again today, but that's boring for the people who showed up, and just as importantly, it's boring for me. So instead, we're going to jump ahead a little bit and see a few sort of beautiful, cute little results in this area that are surprisingly easy to prove. And they use something that we'll also see again a little bit later in the course called the pigeonhole principle. Yes?
So I would have liked to attend the first class, but I didn't based on your message.
So there will be a video of that class online. The sound quality is a bit off, but it's not critical. There's only one result that we used. Okay. So before I do this, let's start with like a really unimpressive magic trick. Okay, U4 and U3. I would like each of you, don't tell me, pick a number, an integer, 1, 2, or 3. Okay? And let me use my my psychic abilities to divine what you each picked. One of those numbers was picked at least 3 times. You tell me your number. 2? 2. You? 2. You? That's 1, 2, 3. And you? 3. Great. So indeed, some number was picked at least 3 times. So a couple of things about this trick. I have utter confidence that it's going to work because of what's written on the board here. And in fact, notice that I didn't make you write down your number so that you couldn't change it after the fact. You guys were giving your numbers one at a time, and if you had been trying to break my trick, well, you should have lied about the number you picked and just said it was something different. Even then, it still would have been true. Okay? So why is that? Well, that's because there were 7 of you and only 3 numbers to pick from. Okay. And so in the language here, written on the board, if I have a set of pigeons, that's you guys, the 7 pigeons, set A of pigeons, and a set B of holes, and every pigeon flies into a hole, so in this case the holes are the integers 1, 2, and 3, then some hole will contain at least the size of A over the size of B pigeons. So this is 7 over 3. And not just 7 over, so that's also true, but the number of pigeons in any particular hole is an integer, and I'm saying it's at least the ceiling of that thing, right? So 7 over 3, that's 2.3333333. Well, I can't have 2 1/3 pigeons in a hole unless I use a knife. But that's not a nice thing to do. So the number of pigeons in any particular hole is an integer, and so the ceiling of that is 3. So I knew that no matter what you picked, there was going to be some number that was picked 3 times. Okay. So this is the sort of informal thing. So some hole will contain at least the number of pigeons divided by the number of holes, ceiling pigeons. And some hole will contain at most the number of pigeons divided by the number of holes, the floor of that. Okay. So is that clear? Okay. And this floor and ceiling notation is not new to you. This is the ceiling is the smallest integer, which is bigger than or equal to its argument, and floor is the largest integer, which is less than or equal to its argument. So the ceiling of 2.333, smallest integer that's bigger than or equal to 2.3333 is 3. Okay. All right, so this is sort of the plain language version of it. There's a more, let's say, abstract version where we can say let A and B be sets, and F from A to B be a function. Then 1 there exists some, let's call it x in B such that f to the minus 1 of x, the size of that thing, is bigger than or equal to A over B. And okay. So this is a sort of way to present the same thing using more mathematical terminology. And the picture that you should keep in mind is there's a set A. These are the pigeons. And there's a set B. These are the holes. F is a function from A onto B. That means for every pigeon, there's exactly 1 hole that it goes to. Maybe these two go to the same hole. So something, this is the picture to keep in mind. So if this is some value A and A, then over here, this is f of A. And so, this could be A1, then this is f of A1. This could be A2, this could be A3. This is f of A2, which is also happens to be equal to f of A3. And this f to the minus 1 business means you take something from B and you look at the set of things that map onto it in A. So it's the inverse of that function. And functions, if you've done something like, in algebra and calculus, we talk about invertible functions. But here, the inverse of the function just means the set of things that happen to have that value under the function. Okay? So here, this is for example, the x that the theorem is talking about. And f to the minus 1 of x is A2 and A3. Okay? So just write that down. Right, so pigeons going into holes, and it says that there's some hole that contains at least, and A over B here, it's like the average, right? The average number of pigeons per hole, right? You take the number of pigeons and divide by the number of holes, and something is at least the average, and something is at most the average, and you get to take floors and ceilings because we have integers. So any questions about that? All right, how would you prove such a thing? Yep.
Maybe like informally you could prove that if they had the same cardinality, both sets, and you spread them out equally, then if you added one, it would have to go somewhere.
Okay, so somehow you want to compare the cardinality of the sets. And indeed, right, if A and B are the same size, well then all you can say is there's like one pigeon per hole at least, and also at most. And then, well, if you add one more pigeon, then it has nowhere new to go. So there's that kind of idea. But here's a sort of a short way of doing it. So just look at how you can compute the size of A. Well, the size of A is you just add many elements from A mapped to X. Right? So here A has size 1, 2, 3, 4, 5, 6. And over here, 1, 2, 3, 4, 5, 6. Okay? So this is the size of A is 1 plus 2 plus 1 plus 1 plus 1. So you agree this is a way of writing the size of A. It's just by counting for each element in B how many elements of A map to it, because every element of A maps to exactly one element of B. Okay. Well, and so now that we've sort of recognized that, so here's the proof of 1, and it's by contradiction. Assume that for every x in B, the size of f to the minus 1 of x is smaller than the ceiling of size of A over the size of B. strictly smaller than. So if it's strictly smaller than this expression, then since the size of f to the minus 1 of x is integer, that means that the size of f to the minus 1 of x is less than size of a over size of b. Okay. So let's pause for a second and think about why that's true. So we assume it's smaller than the ceiling of a over b, and it's an integer. So that means that if it is well, if it's not bigger than or equal to a over b, it can't be equal to a over b. It can't be equal to the non-floor, non-ceiling version of a over b. So it's actually smaller than that. Okay? So it just takes a few seconds to convince yourself that this is the case. Okay. And now we're basically done because we're going to use this thing. So let's write down what we know. So what we know now is that the size of A using this is the sum of x in B, the size of f to the minus 1 of x. But now we know that for every x in B, or we're assuming that for every x in B, it's smaller than a over b. So that is smaller than sum over x in B of a over b. But wait a minute. This thing here, this is a sum, and the number of terms in this sum, the number of things we're adding up, well, there's one for each element of B. So actually, the number of things we're adding up is just this number B here, right? So this thing here, if we want to be really is that, which of course simplifies to the size of A. So let's see if this makes sense. Size of A, so if we read this from left to right, the size of A is less than the size of A. Is that possible? No. A number can't be less than itself. Okay? So that means something is wrong. And what's wrong is, well, we made an assumption here that this was the case. Why did we make that assumption? Well, because if this assumption is not true, then the theorem is true. Then this part is true, right? I mean, if they're not all smaller than size of A over B, then one of them is greater than or equal to size of A over B. Okay? So assume that the thing that we're trying to prove is not true. That's what we did here. And we derived a contradiction. So it must be that the thing we're trying to prove is true. Because assuming it's not true leads to a contradiction. That's just the proof by contradiction. Okay. So we write a little lightning bolt, meaning that's the contradiction we're looking for, and the proof is over. So that proves this part one that says the number of pigeons in some hole is at least the average. And if you want to prove part two, the proof looks exactly the same. You just switch less than for bigger than everywhere in this proof. So any questions?
I'm just curious,
Yeah.
because you counted the f of a, like on the B portion.
Yeah.
You counted that twice, even though it's just 2 going into 1 out.
Well, because I want an expression for the size of A, and one way to do that is by, I mean, it's a bit ridiculous because you can take every element in A and just add it once, and that's how you get the size of A. But if you do this, the same thing by counting for every element in B, how many elements of A go to it, you get the same number, right? And the reason that that's useful for us is because this is really a question or a theorem about how many elements of A go to a particular element in B. And if too few everywhere, then there's just, that means not everything in A went to B, basically. Okay. Okay. All right. So that's the statement of the theorem, and the proof of the first half and the second half. As I said, you just invert the less than and greater than signs everywhere. So let's see what this theorem is useful for, other than these pseudo magic tricks with people who seem to think alike very much. So here's one, and I'll write the plain language statement as well as maybe a more formal statement, or the mathematical language statement. So we saw before this Ramsey theorem about in any group of people, there are in any group of 6 people, there are either 3 mutual acquaintances or 3 mutual friends. So here's another pseudo theorem. Which says in any group of people, of, let's say, n bigger than or equal to 2 people, so a non-trivial group, there are 2 people who have the same number of acquaintances in the group. Okay? So that says if I take all the people in this room, some of you have been introduced to each other before in the past. That means that you're considered acquaintances. So it's a symmetric relationship. If you were introduced, if I was introduced to you and you were introduced to me, then we're acquainted. And otherwise you're not acquaintances. So I claim that there's 2 of us in here who have the same number of acquaintances in the room. Okay? So here's the more mathematical statement of the theorem. In any graph G, with n bigger than or equal to 2 vertices, there are 2 vertices of the same degree. Okay? So graph is this thing with vertices and edges, and degree. The degree of a vertex is the number of edges incident on that vertex. So let's draw an example. So there's an example of a graph, and if I look at the degrees of the vertices, this has degree 1, this has degree 1, 2, 3, 4. This has degree 1, 2, 3, 4. We already found it. This has degree 1, 2. This has degree 1, 2, 3, 4, 5. This has degree 3. And this has degree 3. So in this particular graph, we managed to find two vertices, that's two pairs of vertices that satisfy the condition. This one and this one each have degree 4. This one and this one each have degree 3. So this is the graph where the vertices are people in the first version of this thing, and there's an edge between two people if they're acquainted. Okay? And we want to prove this using the pigeonhole principle. So what are the pigeons in this problem? Yep.
Are the pigeons the vertices?
Yeah. So the pigeons are the vertices, or if you like, the people. So let A be the vertex set of the graph. And notice that the size of A, we have a name for it. It's n. All right. So what are the holes then? Yep.
Are the holes the edges?
No. So we're trying to show that there are two vertices that have the same degree. Which sounds like we're trying to show that there's two pigeons in the same hole. Yep. The degree of a node is the hole that it goes into. Okay. So let B the graph has n vertices. Can it have vertices of degree 0? Yep.
Some of the writing on the right side is quite small.
Okay, yeah. So A is the vertex set of the graph, and B is the set of, you can also come closer, that'll change the angle, but yeah. Maybe it's on the video because it's lower, anyway. A is the vertex set of the graph, and B is the set of possible degrees. I'll try and keep it below some line in the rest. So can there be vertices of degree 0? Nothing says that can't happen. Can there be vertices of degree 1? Yeah, there's one in this example. And certainly vertices of degree 2 are possible. So we can get degrees as low as 0. How high can they go? Yeah. N minus 1. All right. And then we'll say let for each V in A, vertex in A, let f of V equal the degree of V. V. So what's this f now? F is a function from A onto B. All right. We know the size of A is n. What's the size of B? Yeah? N. Because it starts at 0 and counts up to n minus 1. That's actually n values. So size of B is n. All right, good. Now we can see if the pigeonhole principle is going to work for us. So what the pigeonhole principle says, well, we can find a degree that there are n over n vertices with that degree. So what do we conclude from the pigeonhole principle is that there exists some degree in B such that f to the minus 1 of d, size of that, is bigger than or equal to the ceiling of n over n, which is the ceiling of 1, which is 1. But I want two vertices of the same degree, not just one vertex of the same degree. So, like all good theorems, it's an easy application of something also easy, but it's not immediate. We don't just get this by blindly applying this thing. We need to make we have to do something slightly more clever than this, because all this says is that, yeah, there's a degree that it shows up at least once. But that's really trivial, right? I mean, as soon as there's any vertices, any vertex, it has a degree, that degree shows up at least once. So we need to be more clever. All right. So far so good. We'll back up a little bit. Okay, so case 0 is the graph contains a vertex of degree n minus 1. So, if you look at the graph, there's a vertex that's connected to every other vertex. So, in that graph, are there any vertices of degree 0? Nope. They all have degree at least 1 because they're all adjacent to this guy, and this guy has degree n minus 1. So in this case, there are no vertices of degree 0. But that means that f is really a function from A onto this set, 1, 2, 3, up to n minus 1. This set here only has size n minus 1. Okay. And so now we can say, by the pigeonhole principle, there is some D in, we were calling it B, such that f to the minus 1 of D is bigger than or equal to the ceiling of n divided by n minus 1. So this number here, it's bigger than 1, and so when we take the ceiling, it's at least 2. So that says there's some degree that there are two vertices of that degree. Yeah?
What's PHP?
The pigeonhole principle.
Oh, okay.
Yeah. Let me. Okay, but now we're in this mode of doing case analysis. So case 0 is the graph contains a vertex of degree n minus 1, and case 1 is not case 0, there is no vertex of degree n minus 1. But that means f is a function from A onto, maybe there's a vertex of degree 0, but there's no vertex of degree n minus 1, so the highest degree is n minus 2. This is also a set of size n minus 1. And we apply the pigeonhole principle to it, and we get exactly the same result. So I think that's beautiful, don't you? Not an obvious result at all. Even when you know that it's a proof that goes by the pigeonhole principle, it's not even obvious what the proof is, because the direct application of the pigeonhole principle doesn't work immediately. Yep.
Like that A is mapping onto all of the possible degrees there?
Yep. Yep. So this is, right, if I say what's f of this vertex, f of this vertex is 1. F of this vertex is 4. F of this vertex is 4. And indeed, f to the minus 1 of 4 is the set that has these two vertices in it. It's the thing we're proving exists. So just sort of an interesting fact that there are two people in this room who know the same number of, or acquainted with the same number of people in this room. Not necessarily acquainted with each other, but they know the same number of people in the room. Okay. But it definitely relies on the fact that this acquaintance relationship is symmetric. And that's because, where did we use that? We used it right here, that if we have somebody who's acquainted with everybody, then everybody is acquainted with that person. So there's nobody who's acquainted with nobody. That's the place where the symmetry of this acquaintance relationship is critical. Okay. Good? All right. Let's look at another application. Here's a theorem. Every sequence of n squared plus 1 distinct numbers has an increasing or a decreasing subsequence of a length n plus 1. So if I give you a long sequence of numbers, they're all different, then inside that sequence, I can pick out a subsequence, so select some of the numbers, so that those ones that I selected, they're either strictly increasing or strictly decreasing. And the number that I'm able to choose this way is approximately the square root of the length of the sequence. Right? So if this is the length of the sequence, then this is approximately the square root of that, right? Okay. So I don't know. It's hard to do examples without making. What number am I missing? 1, 4, 2, 3. I got 10, I guess. All right, so let's see what this is. So this is a sequence of 10 numbers. 10 is equal to 9 plus 1. So that looks like that. So this says that I should be able to find 4 numbers here that are increasing. Pick out 4 numbers here that are increasing, or pick out 4 numbers that are decreasing. So let's say, here's 1, 1, 2, 3, and 10. So there's an example where it works. It better work for every example, otherwise its theorem is not true. But so that's what I'm talking about. Here's my sequence of length n squared plus 1, and here's my subsequence of length n plus 1. In this case, it happens to be increasing. There's plenty of other ones, I guess. 1, 4. It's clear what the statement of this thing is. So let's prove this. Proof. Let's call the sequence A1 of numbers, A2, A3, up to A n squared plus 1. And now let's do something really non-intuitive. This one I really like because it's kind of an easy proof, but easy after you've seen it. Not so easy to come up with yourself. For each I in 1 up to n squared plus 1, let f of I equal the length of the longest increasing subsequence that starts with AI. Okay? It's a really funny thing. So for each of these positions here, I'll look at this thing and say, what's the longest increasing subsequence that starts with 1 here? Okay, so I get some number, and actually longest increasing subsequence, even when you're given the starting point, is not so easy to solve. It takes time to solve, so we won't write down all the numbers. Here I see one of length 1, 2, 3, 4, 5, 6. So from this guy, I can make an increasing subsequence of length 6. From this guy, I see maybe 4, 4, 1. So 1, 2, 3, 4, 5. Only increasing. So this. Oh, did I go 9, 8? Okay. Yeah. So then this should be only 5, and then this should only be 4. 1, 2, 3, 4. Yeah, okay. So that's 5. This one's 4. From here, I should be able to do exactly the same, right? 4. From here, 7, 8, 10. From here, 6, 8, 10. From here, 5, 8, 10. From here, 3, 8, 10. From here, 9, 10. From here, 8, 10. And from here, I can only get a sequence of length 1. Hopefully those numbers are correct. I'm not sure. Okay. First one is 5. 1, 2, yep. 3, 4, 5. Yeah. I think so. Okay. All right. So we'll just define this f of I. And now we're lucky. Well, if f of I is bigger than or equal to n plus 1 for some value I, then we're done. So here already, in this example, we're already done when we look at f of 1, because here we found it starting with 1, there is an increasing sequence of length 5, which means if we just drop the last number in it, it's an increasing sequence of length 4. And that's all we promised, is either an increasing or decreasing sequence of length 4. Okay. So if f of I is bigger than n plus 1 for any value of I, we're done. We found the increasing sequence that we're looking for. Otherwise, so if we're not done already, then f of I is less than or equal to n for every value of I. Okay, good. So what's that saying? Well, that's saying that actually there are no long increasing sequences. And what I want to use now is somehow know that we're talking about the pigeonhole principle here. So I want to use somehow that there's a whole bunch of i's whose longest increasing sequence that starts at I is the same, has the same length. So for example, here I see a whole bunch of places where the longest one here is of length 3, the longest one here is of length 3, the longest one here is of length 3, and the longest one here is of length 3. Do you notice anything about those numbers? The ones that generated these things? They're decreasing. Is that an accident? No, it's not. Because if the longest increasing sequence that starts here has the same length as the longest increasing sequence that starts here, that means this one must be bigger than this one. Because if it was smaller than this one, you just take the sequence that starts here, put this before it, and you get something longer. Okay. So it's sufficient now for me to show that, well, there's a whole bunch of these things. There's n plus 1 of these things where the longest increasing sequence has the same length. That implies that they form a decreasing sequence. Okay. And why is that going to work for us? Well, what have we got? Well, we've got a bunch of pigeons. They're flying into a bunch of holes, and there's not that many holes anymore. Okay. So what is f? F goes from a set of size 1, of size n squared plus 1 onto, well, everything starts a sequence of length at least 1. Even the last one is a sequence of length 1. But the largest one, the longest one, is of length n. So all these f values now are between 1 and n. There's only n of those, and there's n squared plus 1 of these. So therefore, there exists, so by the pigeonhole principle, there exists some I, let's not call it I, let's call it D, such that f to the minus 1 of D, the size of that is bigger than or equal to size of A, n squared plus 1, divided by the size of B, which is n. You take the ceiling of that, and then you convince yourself that that is bigger than or equal to n plus 1. Okay. Why is that? Because n squared over n is n. N squared plus 1 over n is bigger than n. And then you take the ceiling, so you get the next integer, which is n plus 1. Yeah?
What does ST mean again?
Such that.
Such that, understood. Thank you.
Okay. So that means we can find some integer between 1 and n where there are n plus 1 values of I, such that the longest increasing sequence that starts at AI has exactly that length d, and all of those locations, they must form a decreasing sequence, and that decreasing sequence is of length at least n plus 1. Very cool and very useful theorem. You know, and for an exercise, try and write down a permutation of 1 through 10 where the longest increasing sequence is of length 4 and the longest decreasing sequence is of length 4. Just to see that it's tight. Okay. Questions? Okay. So we have time for one more beauty. So this is a very famous theorem, this here. It's called the Erdős-Székely theorem. If some of you are Hungarian, you'll know where to put the accents on the second name. Anybody heard of this guy before? Yeah. Seen the movie or something? No. So Paul Erdős is a super famous mathematician. He died quite a while back now. At least he died in my lifetime, at least, so not that far back. But he was famous because he just basically kind of wandered the world doing mathematics. He didn't really have a home. He just stayed with other people, did nothing but mathematics, working with many people. He has a huge number of collaborators, a huge number of research articles. And you know, the thing people like to remember about him is that he lived to be about 85 or so, and he spent like his last 40 years using Ritalin and what's the other one, Adderall, as a stimulant, so that he could work about 18 hours a day on math problems. But yeah, he's famous, you know, outside of mathematics, sort of that's the story. But inside of mathematics, he's had profound contributions to many, many branches of things. This is just one sort of really important, simple thing that he and Zekarosh discovered. Okay. And let me make sure I get the constants right here. So let m equal 1 up to 2m, and let, I don't know, c be a subset of m with the size of c equal to m plus 1. Okay? So setup is I give you the integers 1 up to 2m, so up to an even number, and then I take a subset of those that contains just one more than half. X not equal to y, x in c, y is also in c, and x divided by y is an integer. So I give you this, take some subset of the integers 1 up to 2m. So let's take m equals 5. So the integers are 1 through 10. And I have to take 6 of them. And there will be a pair where one divides the other. So I don't know, give me 6 integers from 1 to between 1 and 10. Yep. 1, 3, 5, 6, 8, 1, 2, 3, 4, 5, one more, 7. Okay. So 1 was a bad choice because 3 divided by 1 is an integer, so we win there. Let's scrap that one. Give me another one. 10. 10 divided by 5 is an integer. So we scrap that one. I don't know, which one should we scrap? 5, I guess. Give me another one.
Sure.
Yeah.
There's 6 divided by 3, now it's 2.
Yeah, and 6 divided by 3, so we're trapped. We're stuck here. So, and if we better be, because the theorem is supposed to be true. But how do you prove this? And it's not just true for 10. It's true for any even number. So here's the proof. I don't know, let's give a name to C, the elements in C. Let's call them C1, C2, C3, up to C, m plus 1. And now, for each I in 1 to m plus 1, write Ci in the following way. It's equal to 2 to the Ti Qi, where Qi is